Hi guys, can you hear me?
Hello.
Why is this camera so dark? Can you see some movement behind the camera?
Yeah, we can see you. It's kind of dark.
Yeah, I
That's
can
not
see
bad.
you.
Okay.
Where is Dax?
You only have one camera so far. Noel, are you on a
Well,
camera or no?
one other person's here, but I'm not sure.
I'm just running off my laptop at home, so
Oh, you
the
are?
webcam isn't working on this one.
Okay. We missed someone last time. We missed actually. Who was absent? It was two people, Griffin and Philip.
Where's Dax?
Yeah. So we missed the other two actually. We missed Griffin and Philip. And they're still missing today.
Yeah. Weird.
Let me see if I put the blinds down, it gets better or not. No, it doesn't. See, the problem is when I do Adobe Connect before this, unless I reboot the machine, the camera doesn't get reset, which I forgot to do. So let's see. Let's continue. I don't know what happened to them. But in the meantime, any questions or anything we were trying to do? So let's finish up this topic. I actually posted the assignments. You should have seen them. I mean, did you see them?
Yeah.
There are two of them, right? One was quick sort, and the other one was. We'll talk about what the other assignment is all about. It's about priority queues. So we know what a heap is. A heap is a structure such that the parent is higher than the children. Right? So we always maintain that every point in a heap, the parent is higher than the children. Right? So there are two main operations that essentially manage. So we can take a heap and translate it and put it into an array. Right? So the advantage of a heap is that we don't have to create a special structure for it. We can always translate the heap to an array. And remember not to use the 0th position, because the first position, because we have this swim and sink, if you keep multiplying by 2, you'll never get there anywhere from 0. So the children are at the location 2k and 2k plus 1, and the parent is at k divided by 2. So there are two operations that's essential for it. One is the swim, which actually you insert it at the very bottom, and then all you're trying to do is compare it with your parent, and if you're higher than the parent, go up and move the parent down to where you are. Right? You keep until you reach the root, or until you find that the parent is higher than you. And that's what the swim operation is. Right? I will use the swim operation to do the insert. So the inserting is exactly that you insert it as the last element of the array. If you're inserting elements, you insert it as the last element of the array, and then you swim the thing forward, like swim it up. So we're going to insert S, then compare it with the parent, and then move it up all the way. It's a very simple operation to move. Right? Keep swimming all the way until you reach where you need to be. Right? So in this case, we have the inking. Where's my mouse? Oh, it's here. Right? So in this case, we use the we insert S as the last element, and then we swim it up. Swim H, compare it. S goes up, H comes down, and then with P it goes up, P comes down, and then with T it doesn't go do anything. It stops there. That's the end of swim. That's the end of insert. Right? So to delete, what we do is we go the other way around. Just to recap what we did, to delete, we sync. Right? So deleting in a priority queue is always removing the first element. Right? So we're removing the so that's what a priority queue is. A stack is something. So stack has, so these are all collections, right? A stack has the property that is last in, first out. It's not how you put things in, it's how you take things out is what matters. So it's based on how you want, because if it's in the collections, I don't have to worry about it. When I'm taking things out, if you want the last thing to be the first one out, use a stack. If you want to have a main first in, first out, use a heap, use a queue. And if you want the element with the highest priority, use a heap. Right? So you're using a heap. So to remove it, remove the
I'm pretty sure that's it. Can we just resolve if he doesn't come back? We're just gonna stay here for an hour. Yeah, I'm absolutely fine with that.
My computer.
Anybody else here in the call?
They can't hear.
Not either they could.
No, because the call isn't
Their
actually.
recording is on. I don't know.
Yeah, but the call's not actually happening.
I can hear you.
Oh, okay.
See?
Never
I
mind.
told you.
Fuck. So how are you doing today?
I've been at home because I've been feeling sick the last few days. Other than that, not too bad.
That sucks. Okay. So
Is he's oh he's back.
Yep. So what happened?
I don't know.
you vanished for a while.
well, on my side, it was you who vanished. It's a relative thing. So you are frozen in time. For me, I saw the frozen stuff, and I didn't see anyone moving. So where did I vanish? Around syncing?
Yeah.
Yeah.
Right. So the important thing here is to see the second part of this thing. To see, so when you multiply 2k, you automatically point towards the left child. So you're going comparing the left child and the right child, 2k and 2k plus 1. The left child is always 2k, and the right child is 2k plus 1. Right? So you multiply both, and if the left child is smaller than the right child, increase by 1. So you always want to promote the largest child up, and the parent. So if the parent is smaller than the children, then you want to promote the largest child up. Right? So that's what the j plus 1 is. So you promote the j plus 1 by promoting it here. That's a j plus. So increase. So now you just if the left child was larger, then you're going to go down the left tree. If the right child is larger, you're going to go down the right tree. Right? So you increase it, and then if it is not less, that means you can now stop, because both children are smaller than you. So you're essentially comparing yourself with the largest child. First compare the two children, find out who is the larger one, and then compare the parent with the child. And if the parent is still smaller, then you exchange. If not, you're done. You break and get out. Right? So that's what the sync operation does. So you can sync, and using the sync operation, now we can do a delete, remove, or delete maximum. Delete maximum is always remove the first one, take the first one out. That's what remember the key, because that's what you want to return. Now take the last child and drop it at the root, and then sync it down. Right? So if you're going to remove T, remove this T, remove that, take the last child, which is H, and then make that as the CEO, and then ask everyone else to push him down until he finds his right position. Right? So remove the last child, decrease n by 1. You don't want to go beyond n. You always maintain a compact list. So decrease this by 1, and then sync down. Keep syncing down. And the last thing you want to do is, you also want to do this and say, make that last element where the child was, that needs to be now made to null. Because the child it was an array, so you want to make that. If not, the garbage collector, you may have decreased n, but the garbage collector still doesn't have the ability to remove the unwanted node. Right? It still keeps a reference from the array, so therefore it ends up keeping nodes that are unused, and then you remove the maximum, return the maximum. That's what syncing is all about, and removing and deleting maximum. Right? So that's essentially what a priority heap is. A heap is a data structure that it's not a first in, first out. It's not a last in, first out. It's the highest priority to be removed every time. Right? So that's all these are the main methods that you'll look at when you look at this. So we know what you need to create. At a minimum, a heap should support a constructor, an isEmpty method, an insert method, a delete method, a swim method, a sync method, and of course these are private methods. These are all private methods to maintain them. A less than an exchange. These are you can certainly have other things added to this, but this is what makes it a heap. You can have iterators, you can have other things, two-string methods, you can have all of that. But a heap, at a minimum, should support these. So, and we can, without kind of thinking too much, we know that what's the time complexity of this? Because the heap insert takes a time, log n. Right? Because you're traversing up one of the branches. The height of the tree is always log n. So the worst case insert would be log n, and delete also is log n, because you have to delete it and sync it from the root all the way to n. So there are other types of heaps that we essentially based on the same ideas. We'll not kind of discuss them. We'll just get to what we want to do. So overall, there are some basic things we have to remember in a heap. The keys cannot be, it's immutable keys, meaning what happens if we change the key? Once we create a heap, you don't want the key to be a mutable key, because once you insert in the priority, the key has to remain. So keys have to be constant objects. Like a string, like an integer, that if you change it, that's not the same object, it's something else. And because in a priority heap, okay, I can ask you, so what would happen if you have a priority heap and then you change the priority of it? You can think about it. if you have a heap, and then if you have the key, and what happens if you can change the thing? If you can change the priority after it has been inserted.
Well, you have to like reorder the whole heap, won't you?
And how would you reorder the whole heap? What would you need to reorder the whole heap? Let's say if an arbitrary node has been changed.
Oh, you just have to sink or swim that node.
Yeah, sink or swim. Yeah, exactly. Right from where you are, just sink. Like whether you have to swim up or swim down, because you're not worried about the rest of the tree. All you have to know is where you are with respect to your parents and your children. And you just have to sink or swim. But it's typically like you want to use immutable keys. Okay? And similarly, what happens when you remove an item? Remove an arbitrary item, like remove something from the middle of the heap.
Would you have to like swim everything below it, or sink or swim everything below it?
In a way, what you can do, you can take the last item and put it where the item that was to be removed, and then sink it or swim it, right? So you just put it wherever that item was removed, and then just insert it in the right tree along that path. Make sure that you remove the last item, because we don't want to remove holes in it. Like it's an array, so you don't want to put holes in it, so we want to remove that item. Take the last item, put it to the item where it needs to be, where the item we just removed, and then sink it or swim it. Right? So usually keys are immutable. So best practices, immutable keys. Underflow, overflow, we can easily take care of them. We can throw an exception if you're trying to delete from an empty queue. And overflow, we can always use an array list or some type of a thing that automatically resizes the array so that it never gets up at overflow. And then, of course, if you want to change it to a minimum-oriented key, instead of having the less, replace it with a greater. I think if your priority is minimum-oriented, you change the less to the greater, and then the structure would almost remain the same, except in this case, the parent is always smaller than the children. Right? So you can have a key thing that's either minimum oriented or maximum oriented. Things don't change too much. Okay? So there are these. Okay, let's skip the vector. So now, how do we use a heap to sort? Can we use a heap to sort?
If you're just sorting for like value size, theoretically.
Yeah, let's say you have the keys and you want to sort the keys.
Well, I mean, at this point I'm just reading off the PowerPoint, but
you definitely
you just keep removing the top one and then
order them.
Either sink or swim.
Yeah, kind of like that, right? So, I mean, the sorting part, well, so you keep removing from the top and then you start sinking. But before that, you need to create a heap. Suppose someone gives you an array of unsorted items. You need to create the heap first, right? So you need to, because you cannot sink, I mean, unless you have a heap, you cannot remove. So if it is an array of unsorted items, then you'll have to create a heap first. Right? So how would you create a heap using an array of unsorted items?
Well, like this is just a guess, but could you just start inserting things into the heap and then like sink or swim them?
We don't have a heap yet. We have an array. Right? We have an array that looks like this, like sort example the way it is. Right? So you have an array that has exactly the same keys. So we remove the first item and we move it around. Right? So we have something like this. So we need to create a heap. So based on this, it's not a heap. If I put this in an array, that's not a heap. Right? So this is certainly not the smallest item in the entire unsorted array. Well, the brute force way would be to create the heap, create a second array, right? And then start inserting take each element from the first array, and then now reinsert it, but this time as a heap. Right? So take the S, insert it into the heap. Take the O, insert it into the heap. So as you are inserting, you are going to be exchanging things. Right? So if you are given an unsorted array, you can always recreate the heap by creating a new array. Take a new array of the same size. Take each element and throw it in. The second one, the elements are going to be maintained in a heap order. Right? So that could be done. The only yes, it can be done. The only problem with that is that it doesn't make it an in-place thought, because now you need an extra array. Right? You need, like, if you have 1,000,000 elements, you need a second array with the same 1,000,000 elements. Right? So it doesn't make it an in-place thought. Right? So one thing you can do is if you don't want to do that, you start reheaping the array itself. You start creating a heap with the existing array itself. So what you do is, let's say you have an element of 11 elements. So you have an array that consists of all the elements like that. All right. So the first one is gone. So it'll be S, O, like that. Have an element like that. What you can do is, what about who else? I want to check. Is well, Griffin is here. Philip is not here. Griffin, your camera is always turned off. You may want to kind of see if you can turn it back on. I can't see you. Hi, Griff, can you hear me?
Sounds like he's not there.
Oh, he's chatting. He's saying, yes, I can. We have hardware problems at the school.
Okay. So you want to tell them and fix that, like he's texting. So I have to switch. Yeah, right? So as long as you can hear, that's one important thing, but I also want to know that I can see what's happening. So what you can do is, so you can make a heap out of this array without using extra space, is to start from somewhere, like start from the middle element. Start from the middle element and then start a heap going backwards. Like in this case, let's say, for example, you want to take this and make an in-place heap like this. Right? Without having an extra array. So you can start off like this. You can start off with the E. I think the next slide has it. Start with a middle element, and what you do is make a little heap out of this one. Right? So because you're starting with middle element, which is there are 11, so you're going to start with element 5, and then look at a heap and say, what about 5 and its children? Can I make a heap out of that? Right? So I can take the 5, the element that's at the 5th position, and say, hey, let me compare that with the children and make a heap. So in this case, yes, I need to erase it. So in this case, like 5, the children are 10 and 11. So I create a heap. Right? So 5, so because after 3, so L goes up and the second E comes down. So I create a heap, little heap starting from the 5 element. It's just swapping 3 elements in place. Then go to the element before that. Take the 4th element and make a heap out of that. Right? So T, M, P, that's a heap. So I just leave it like that. So essentially what you're doing is, if you go back, so you're creating a heap from the bottom of the heap. I mean, you can save your time. You don't have to start from, do I have to start all the way from n, or can I start from n over 2? I can start from n over 2 because all the others are leaf nodes, right? So every node after the first half are going to be all at the leaf level. They don't have any more children. So I start at n divided by 2, make a heap out of this, then go to the 4th node, make a heap out of nodes 4, 8, and 9. Then go to node number 3. Right? Go to node number 3, make a heap out of 3, 6, and 7. Then go to node number 2 and make a heap out of the entire thing. Right? Because now we know that these two are heaps. These two are heaps already. Because when we are going from the end, these two are heaps. So now we take the two, we already have built in a right heap and a left heap. Now take the parent node and then make a heap of that. And then take node number 1 and make a heap out of that. Right? So you see, I don't, can you see how it's being done? That I don't need an extra space, right? So you just take, now if it's an array, but we can visualize the array to be an unordered heap like this, like not a heap. Like we can, if you translate the array, which was this, it looks like that. Right? We can visualize. We can visualize the array to. Oh, if it had been written as a binary heap structure, that would look like this. A binary tree structure that would look like this. So you can number the nodes and says, okay, these are the nodes. 1, 2, 3, 4, like that. Start in the middle. Start at element number 5. Take this and look at the two children of that element, which is those two, and make a heap. And then start at element number 4, look at the two children, make a heap. Right? So that way I don't need a second array. I don't need a second array because it's already it's in place sort, right? So that's quite a big improvement in the sense that if you have for 2 gigabytes of space, you don't need an extra 2 gigabytes of space. You can do that. All you need is one extra space to swap the elements and create a heap. Right? So once you create the heap, then the sorting is it's not too bad. Right? The sorting part is not too bad. So now that you know you have a heap, then what did I miss here? Did I miss anything? Right. So this is what the heap sort. Okay, that's fine. Nothing here. Where's my sort? Yes. Right. So the sort is, take the first element. So even this, I want to sort this within the same array. I don't want an extra space. Right? So I want to sort this heap. I'm rearranging the same array back into its own, within the same array. So I take the first element. Now then it's a heap. Take the first element, exchange it with the last element. Take the first element, move it down. Right? and take the last element, which was the E, and move it up and sync it. With one restriction, now your heap size is not n but n minus 1, because you don't want to sync it to the entire. If you sync it all the way down, then you have a problem. So you move it, like if you go back to the, so if this was the array, if you want to imagine this to be the array, and this is where all the elements were initially in a heap order, you take the first element. So this was the entire array. Right? So you take the first element, which was X, move it to the last element, which was E, exchange them. So X goes here and E goes up here, and then sync it, but sync it only up to this much. Right? Sync it only up to that much. So E would eventually go into one of these spaces, but not to the last space. The last place is where the largest element is. So when you sync the E, what would happen? When you take the last element and sync the E, what would happen?
It'd be sorted.
We saw it, T will move up, right? The next highest element will move up, and E will get lost into the heap somewhere where it needs to be. Right? So now take the T, put it now. So now that T will be up, take the T, put it right next to it. Take the last, so T goes here. Take the element that was at T, exchange these two now. And this time you're sorting it into an array of size 1 less. Right? So you're syncing it back into the same array, but your n becomes less and less because you're repacking the from the end. We are repacking the elements with larger elements. Right? So we repack it with larger elements. So eventually you'll get this A, E, E. The array would look like that. Can you see how that's done?
Yeah, that makes sense.
Right?
Yep.
So it's an in-place sort. So you're given an array of an unsorted array. First operation would be to create a heap ordering of the array, which would be to start from the middle element and then start making small heaps, and then you go all the way making the final heap. And then the second step would be take the heap and then rewrite it back as an array. And every time you take the large element from the top, which will be the root. The root would always contain the largest element. Exchange the largest element with the last element on the heap, and then take the last and then sync the newly inserted element into the heap with n minus 1. And n minus 1 gets all the way to 1, and you have a sorted array. So that's what a heap sort is. Right? And as you can see, without proving too much, as you can see that all these are taking in the log n type of thing. It's all log n. Maybe you have to, this is 2 log n because it's 2n log n. If there are n elements, it's going to be 2n log n. But it's log n because you're always going down the tree, a branch of a tree. And the height of the tree is always log n. We need 2 because you need to do it twice. 1 to create the heap and 1 to sort it. So there's an n log n process to create the heap and then n log n process to sort them. So you have a thing of 2 log n. Right? So it is in place. It's guaranteed n place. There's no best case, worst case. It's always the same. Right? I mean, the best would be like you can, if you don't have to swap too many elements, but it's n log n guarantee and it's in place. Right? So this is what heap sort is. we looked at many different sorts. Like this is a kind of a table, okay, which most of them are in place except the merge sort. Merge sort is pretty good, except that it's not in place. We need an extra array, and it also requires a lot of bit of copying operations. Of all these, the in probabilistic and in practice, quick sort is the one. Most people end up using it. That depends on what you want to do. But if you want a heap, like for example, you're maintaining something that needs to be maintained in a heap, then you use a heap. You're not sorting them, you're creating a heap. So that should finish chapter 2. Right? Heap construction takes fewer than 2n, and then it takes 2n log n compares and exchanges. Comparing to this is an n log n worst case. Merge sort, it is not an in place. Right? It needs extra space, linear space. Quadratic is worst case has a problem. Quick sort has a problem. It can end up with quadratic time. This one is both. So it's a kind of a guaranteed thing. Like it's always like it's both. You can look at the extra space requirements and the guarantee of the worst case. Heap sort works quite well. So heap sort is optimal for both time and space, but it doesn't, the inner loop is longer than the quick sort because it had to go through the entire loop. And also the other thing it makes poor use of cache memory. So what is poor use of cache memory? It's not stable because the arranging all takes, right? So what does it mean by poor use of cache memory? You know how computers do cache? There is something called a cache memory in computers. There is like you know what memory and CPU are, right? There's memory, there's a hard drive, right? So if you, I don't know whether I draw this picture before. If I drew this picture before, it's kind of like a CPU is like if you think of a CPU like an office, like there is the workbench. Right, the workbench is where memory is. Memory is the workbench. The bookshelf is the extra storage. Now, what happens is because the CPU itself, there's the CPU out there, and then there is a memory out further away, and then the hard drive, which is actually maybe not even connected to the memory on the motherboard. It's connected out of the thing. The hard drive is away. Right? So there's memory, hard drive. Why is that like that? Right? So there's memory, there's hard drive here. So what happens is, now let's imagine that you are, it's like if you're working, you're working on a workbench and you want to repair things on the roof. Right? So it's like, okay, my workspace is all there at the roof, and your cabinet contains all the tools you want. You don't take all the tools you want. You take the tools you want only. It doesn't have to be the roof. It can be right on the place where you're doing the work. You take the tools all you want, put it on the desk. Right? And if you are working away from it, if you need the screwdriver, like illustration, let's say you're working on the roof and you want the screwdriver. Okay, you take it, go up, use it, and then now you want the hammer, you come down the ladder, put the screwdriver down, take the hammer, move it up, and then you go up, and then now you need the screwdriver back again, or you need the plier, you come back, leave it. So it's a lot of climbing up and down for each one of those things. Right? So you can only take one tool at a time. That's the only tool you can use. So if you're going to carry one tool at a time, you're going to be moving between one. You're back to the workbench, pick up the tool you want, go to the place where you want to work, and then come back, put the old tool, then pick up the next tool, go back like that. Would you work like that? What would you do?
Take the toolbox to the roof with all the tools that I might need.
But I mean, you can't take all the tools. You want to select a few
yes.
tools, right?
You know what you're going to be working on. So you take
Yeah,
what
but
you can.
you may be needing more tools than what you can carry with you, right? So you can either take a toolbox, which is pretty big, or you can wear a belt, a tool belt, right? You cannot carry too many things, but it's still faster than like a toolbox, depending on where you want to, right? So that's what it does. That's what cache is. It has multi levels of cache. It has a tool belt. The tool belt is kind of like right on the CPU. So CPU, if this was a CPU and this is where the registers are, it has a little extra space, right? So you carry something right on yourself, so you can just pull it out quickly. In addition to that, you have a little bucket or a toolbox with the few tools you can carry with you. So they have what's called level 1 cache, level 2 cache, L1 cache, L2 cache, like that. Right? So the L1 cache is right on the CPU. The L2 cache is on the motherboard, but closer to the CPU. And the memory is also connected to the motherboard, but that's a separate thing. Like it's a separate chip that you plug it into the motherboard. Right? So it's like you have things in your hand, plus a few selected tools on the tool belt. That's L1 cache, plus a little toolbox with a few tools. That's L2 cache. And all the other tools you need for the project, that's the memory. That's on the desk. All the big power tools and all that stuff you can. And then, of course, all your collection of tools is what is on the hard drive. So the question is, how would you decide what tools you want?
If the program tell you?
Well, so you have to. So you would find that even if you're working, you might take the tools and find that you don't have the right tools. Right? So you'll make a bad. You'll have to guess essentially. Guess and see these are the tools. Like what? Right? So you kind of say, yeah, okay, this is what you want to do. So we make a guess of the tools we want, take it, and then if you're unlucky, we have to come down. So similarly, when the program is running, it guesses the next set of instructions or the data it needs and tries to move it into the cache. The CPU says, okay, you're reading this part of the memory. I'm going to read a little more and move this entire things into the memory. It's going to now, if you're in a given section of a memory, it says, okay, let me read you the next 100 bytes, because most likely you're going to be needing the next byte afterwards and the next byte afterwards, right? I mean, if it is a program, it's going to be okay. Once you read instruction 1000, the next one will be 1001. Okay? So it tries to grab the adjacent pieces of data and move it into the cache. Okay? Now, if you're lucky and if the data you want is right in your toolbox, which is right in your cache, then you call it a cache hit. You are lucky because what you want is there. You don't have to walk back. If you don't get it, it's called a cache miss. A cache miss, and then in which case you have to go back and empty and bring the new tools, because you can only carry so much. So you go back and bring the new tools. Now, this one makes poor use of cache memory because is it based on adjacent information? Is the heap based on adjacent information?
No, it's not. It's based on
The children.
one element can be n, next element's going to be n divided by 2. So
Exactly.
cache is not going to be
Right.
very efficient with picking that up.
Exactly. The cache is not exactly going to be efficient, knowing, okay, I'm at location 500, so it's going to cache all the one between 500 and 525, but what you want is 1,000 and 1,001. Right? So the data you need are not right next to you. Whereas if you compare that with the other sorting algorithms, they're all based on kind of working around the neighborhood. Right? Working around what's around there. Like they're just sorting little parts of the sort and then moving things like that. So that's what it means by make poor use of cache memory, is because the data it needs are all over the place. It's not it's very difficult to guess what your next need is going to be. Okay? So that's kind of the summary of the sort algorithms we have looked at so far, and we'll kind of stop here. And there are some other sort techniques. This should give us a little breathing room and kind of more understanding of what sort is. And there's some additional sort that's in chapter 5, like bucket sort and bin sort and count sort and all that things. It's essentially, most of them are based on the fact that, like I discussed before, if you have 1,000 students in your school, and if they have an ID based on the social security number, why don't I create 1 million or 1 billion array and then put all of them into the right bucket and then walk back and pick all of them, right? So I can create, like, if you create a 1 billion array so that every social security number has a possible location, and take each one of your student ID and put it into the right box, kind of like a mailbox, right? And then you can walk from the beginning all the way to the end, but you can kind of make it a little more efficient and things like that. You don't have to really keep all of them. You can put multiple things in the bag, put all the A's in this bucket, put all the B's in this bucket, and then resort them. You can do a few things like that. So they're all essentially common sense sort algorithms. Let's skip that and we'll go to the next topic, which is binary trees. So before that, let me give you a brief discussion on that assignment. About, like, the assignment I said was that why do they have this few items, like 10 items or less in supermarket? What's the advantage of having a 10 items or less in a supermarket?
Increases efficiency.
Efficiency for whom?
Those who have 10 items or less.
At the cost of the other people?
Yeah.
Right? Right. So you can see, okay, yes, it's not going to reduce the total work done, right? The total work done is going to be the same.
Yep.
Because you still have to do all the work. It's just that you want to do the easy ones first and then leave the heavy ones for later, the longer ones for later. Right? So the total work done is the same. So the question is, what's the advantage of that? And so that's what I want to see. Can we really say exactly what the advantage you gain is? So the idea is this, that you want to compare 3 different service techniques, meaning you want to serve the data, right? So you create an array of workloads. Let's say we create an array of workloads. Oops, why? I need to get and then you have this. So I'm going to put random numbers here. Let's say 50 for these numbers indicate the amount of time I would need to finish that work. Right? So the first one takes 50 units of time. The second one takes 80 units of time. So it's like if you're measuring the queue, like on a Costco, you cannot say, oh, this person has served so many customers. It's not the number of customers you serve. It's a number of Like some customers come with 3 items and the others come with 300. So you can say, yeah, you only served 1, whereas I served 50. Well, your customers are slow. Now you have smaller customers with few items. Right?
Yeah.
So the service is based on the number of work. So these numbers tell you what the time that's required to service the customer, the work. Right? So you randomly create times in it and put them into a thing. Now we have to look at different techniques. So let's assume that all of them came in at time 0. And all of them came in at time 0. So all of them are in at time. Let's say these are let's say we have 10. Right? And we create a table and see, okay, all of them came in at time 0. Let's analyze when did these people leave? Right? So how many? We have 6 jobs here. 1, 2, 3, 4, 5, 6. Right. So the first one had what time it came in with? What time did it come? It came in at time 0. So all of them came in at time 0. Let's do a first in, first out, like an array list. So what time will the first job leave? Time 50.
Yeah.
Right? So second one has a workload of 80. It comes in at time 0. What time will it leave?
1:30.
1:30. Right? And the fourth one comes in at time, it has a load, comes in at time 0, it leaves, and the time would be 1:50, like that. Right? So we can now add them up and find out what's the average turnaround time or the waiting time within the system is. Right? So because all of them have, since all of them are coming in at the same time, we don't have to subtract the initial time. But so the turnaround time is it's called the turnaround time. That's the time when a job enters the system and the time it leaves the system. That includes 2 components, the waiting time and the service time. And there are 2 components to it. So the turnaround time is when you drop it in and when you pick it back. That's all you care about. Yeah, I came in, I dropped it, I'm picking it 2 days later. That's the turnaround time. The turnaround time has one component, that's the waiting time. How long were you waiting in the queue to be served? And then how long were you being served? The service time. Right? So you can find out, we can measure all of them and see, so the average time, how long it took, we can compute what the average would be for them. And we can compute the average by adding all of them up and dividing it by the number of jobs, and that gives you the average. That's the first in, first out. We can create a heap and put this into a heap and do exactly the same thing, except that this time I'm going to remove the smallest job first. Okay? So I'm going to remove the smallest job first. So all the jobs still come in at the same time. The smallest one is the one that's 10. Right? I go scan through the entire. So if I have a heap, can I remove the smallest one first? Yeah. Minimum heap, just remove from the root and you remove this guy. That leaves at time number 10. Now pick the next smallest one. That will be the 120. So what time will that leave? 30. Right? So next, pick the next smallest one. That's the job with size 30. That will leave at time 60. So this is the time, this is the exit time, where the time that system leaves. That's the entry time, so that's the exit time, that final time. So I can do this. I can keep picking up the smallest job first and then serve them and send them out. And I can do an average turnaround time for these 2. Right? That's the shortest job first. Right? That's using the heap. I'm going to insert things into a heap, right? First so initially create an array of random numbers. Each of them is the time that's required between 0 and 100. So in the first one, you use an array just as is. Second one, make a heap out of the array, use the heap, and then find out which the smallest jobs are, find out what it's going to be. For the third one, we'll use what's called a round robin. So the round robin is like everyone. So you serve the things in the order it comes, but the way you do that is by you have a time slice. So you have a time slice. Let's say you have a time slice of 10 units of time. Right? So you take the first one. So it's round robin. If I'm going to draw this round robin one, this is how it's going to look like. You take the first one. So you serve it. So this is the job number A, B, C. Let's mark them. A, B, C, D, E, F. So you serve A for 10 units of time, and then it's not done, so you put it back in line. It goes back in line, right? Now serve B for 10 units of time, serve C, serve D, serve E, and serve F. At this point, F can leave. F can leave because it's got all the time it needs, so F would be able to leave. Right? Now bring back A again. A, B, C, D. Do we need E? Do we need F?
No, F is
No.
already gone.
F is gone, right? So now A, B, C, D, E. Do we need to serve A back again?
Yeah.
Yes. B, yes. C is not needed anymore because C needed only 20 units of time. So it had two of its time slices. It's done. C is gone. Now bring back D and E. And then go back and start doing A, B, C is not in the list, D is there, E and F are gone because E has there, right? So you do this and find out what time each of these jobs leave the system, right? With a time unit of maybe some, like if you're creating time slice, if your job time is between 0 to 100, you can create a 1/10 of that as the, right? So you create a time unit, service time of 10 units, and then serve through them and see what time these jobs leave, and then make a turnaround time and compare the thing and says which one would be the best for what. So all three are useful, right? So which one do you think is the one you like most?
I don't know. I like round robin.
Then let's analyze it and say, why do you like round robin?
Well, because the ones like the items or the people who take the least amount of time get done in a shorter amount of time than normal, but like the items that take a longer amount of time don't feel shafted.
You kind of feel like a little fairness built into it, right? Like, okay, like, yeah, you don't like this person with 3 carts of things in front of you. Well, I know you have to be served. I only have a milk and egg to take. I don't want to stand behind for so long. But at the same time, you feel like, oh, maybe you should make that person also a little bit happy by giving him a few minutes and then pushing him back. Right? So let's see what the turnaround time is. Right? The round robin is how CPUs schedule jobs. Right? And with a priority meaning even within the round robin, they have a priority thing that if there is something that's with the highest priority comes in, then it gets served first. So yes, because all jobs don't have the same priority. A job coming from the hard drive, or a job coming from the system's clock, or something else needs a higher priority compared to your keyboard input. Right? So there are internal services that require higher priority than the external service, the larger programs. So but everything still needs to work. So what would happen if you base it on priorities?
Lower priority jobs would never get done.
The lower priority ones will not get done because that's what's called starvation. Right? They call it starvation because you'll be standing like for example in school, you'll be standing to make copies, and everyone who comes they say, okay, I'm the instructor, I'm a teacher, you go back. I'm the vice principal, you go back. I'm the principal, you go back. And then you never get to do what you want to do. Right? So you have to ensure some fairness in them too by saying every time you get bumped, let's increase your priority by 1. Right? So that you don't get to stand there forever. The more times you get bumped, then you've been waiting there for so long, go. Like that. Right? So there are different ways of ensuring priorities and service times and preemption, but they are based on these types of techniques. Right? So we'll stop here, and then we'll start the next topic on Wednesday, chapter 3, right? Symbol tables.
Awesome.
Okay. Any questions?
No, I think we're good.
Okay. So let's meet back next Wednesday.
Thank you. All right.
You're welcome.
Thanks. I'll see you.
Yep.
Hi, Grafe, you were able to follow this? You heard everything?